Hey everybody, this is Mike Heumann from G2M Research, and this is our multi-vendor webinar on utilizing HPC scale storage for AI and AI for business intelligence. Our sponsors are Samsung, Weka.io, Datura, and NVMe-oF. So let's go ahead and get started. This is our agenda. I'll walk through some ground rules and a quick introduction of the topic. Following that, each of the sponsoring vendors will talk for 9 to 10 minutes about what they're doing in this area. Then we'll have 3 panel questions interspaced with some audience survey questions. And then we'll wrap up with an audience Q&A for about 10 minutes. When you're doing the Q&A, please use the Q&A window on Zoom to put in your question. That way it doesn't get forgotten, and then we can address it when we hit the Q&A window. We're also recording this webinar, and we'll make the recording available to everybody. That link will get sent out to everybody who registered. It'll probably go out on Thursday, depending on how quickly Zoom turns around the recordings. We'll also send out the slide set as well. So everybody should get that is registered. With that, let's go ahead and get started. Our panelists today, we have Rob Davis, VP of Storage Technology from NVMe-oF. We have Young Pak from Samsung. He's Senior Director of Product Planning. From Weka.io, we have Shailesh Manjrekar. He's Head of AI and Strategic Alliances. And finally, from Datura, we have Keith Clear, who's the CEO. And as I said, I'm Mike Heumann, I'm the Managing Partner at G2M Research. So if we look kind of at AI, its value for business and its adoption, it's kind of interesting. It clearly can have a big impact on business. And we all know the stories about e-retailers and other people using AI to spot trends, to ensure that they have the right amount of inventory where they need to. A lot of things that have been used with business intelligence and data mining before, AI's kind of jumped in and started to take that stuff over. Clearly, there's much more improved analytics we can see on the chart here. The improvements that happen, or in some cases where AI itself can be the only way to capture that value. There's only a few percentage of problems, about 15%, that can be captured with non-AI techniques that AI can do as well. So it clearly provides a lot of new business value. However, if you look at kind of the percentage of companies that are doing AI, it's very uneven. So if you look at large enterprises, at least half of them have at least one instance of AI in their business process, but really only about 3% have integrated across their entire workflow. So there's definitely toes in the water, lots of toes in the water, but nobody's made the big leap all the way in so far at this point. There's a couple of reasons for this. One of them is AI is often perceived as being hard to do. And looking at some of the different data out there, there's several reasons why people kind of have said this. And these are some of the things we'll be talking about as part of this webinar as well. First is lack of an overall corporate AI strategy. If you don't know what you want to get out of AI or how you're going to use it, your desire to jump into something as complex as AI might be a little muted. Constructing deep neural networks and other AI frameworks is often considered an art. We'll have at least one of our vendors talk about that, and I think they'll probably tell you it's easier than you think it is. One of the last things, building training and validation data sets tends to be a large challenge. I did a lot of work in product marketing with Cylance, and they used AI for security. I know how much effort and how many people they put into training and validation data sets. So it's definitely a big issue, and it has a lot to do with the performance and success of AI projects. So some of the adoption hurdles and costs: data acquisition, actually getting the data for your data sets. Scaling your storage and your performance for that data can often be a challenge. Data networking as well can be a challenge, and lack of computational speed. So with that, let's go ahead. I'll turn it over to Rob Davis. Rob is VP of Storage Technologies for NVIDIA Worldwide. He's part of the networking business unit. Let me give you control, Rob, and you can go ahead and get started.
Great. Thank you, Mike. And thank you also for the opportunity to present on this G2M virtual event. For my part of the presentation, I'm going to focus on 2 of those adoption hurdle bullets you just showed. The data storage scale and performance, and data networking performance. All right, so at NVIDIA Network Business Unit, we know a lot about moving storage data fast. And as this Forbes article detailed, storage is an important part of AI and ML applications. And the more storage, the better. Andrew Ning, who teaches computer science as a professor and machine learning expert at Stanford, is quoted as saying, "It's not who has the best algorithm that wins, it's who has the most data." This graph from my CEO's keynote at Virtual GTC last week shows how companies have moved from processing gigabytes of data with CPUs to hundreds of terabytes of data with GPUs. One example is a recommender system. These systems play a critical role in driving the user engagement on online platforms. Depending on the website's business, they select a few goods, relevant interests, potential friends, or services from the exponentially growing number of available options to show the user. According to a recent BrandWatch article, Facebook generates 4 new petabytes of data per day. Just to imagine what the data set size for a recommender system there might be. So how do we get those petabytes of data into the GPUs? To explain that, let's look inside an NVIDIA DGX2 at the storage data paths and see how the local and remote storage is connected. Of course, I'm using the DGX2 as an example because I work there, but the principles are the same for other GPU system architectures. There are basically 2 ways to get the storage data into the GPU's memory. One is internal storage on the NVMe SSDs across a PCI bus, and the other from external storage through the InfiniBand or Ethernet adapters. Let's first look at the storage data path from the NVMe SSDs to the GPUs over PCIe. Every pair of GPUs in a DGX2 has the potential of 12.5 gigabytes of bandwidth from those SSDs. And as you saw on the last slide, a system can have, the base system has 30 terabytes of internal NVMe SSD storage. The other storage data path uses network storage connected on either Ethernet or InfiniBand. It can provide up to 25 gigabits per second of storage bandwidth to each pair of GPUs, double the local storage capacity of the internal SSDs. Of course, InfiniBand provides the highest performance and lowest latency because it was designed for the HPC market. But the same wire speed Ethernet network can come within a few microseconds of InfiniBand performance when they are using low latency Ethernet and adapters like Spectrum and ConnectX video, along with Rocky RDMA over Ethernet-based storage protocols like NVMe over Fabrics and NFS over RDMA. It sounds like we need to...
I think we have some people talking there. Could you guys mute, please? Unless you're presenting, thank you. Go ahead, Rob. I think you're good to go.
Okay, cool. Because we can network the storage, its capacity is now virtually unlimited. And network storage brings other advantages as well. For some reason it stops letting me advance. There we go. And network storage brings other advantages as well. High availability with backup and replication management. High utilization. One example is less time wasted loading the data set into the local GPU storage, and lower TCO. By using network storage, you need much less local storage, which translates to lower power, less cost, less cooling, and easier maintenance. Basically, you get all the features SANs were invented 30 years ago for. The network also disaggregates the storage from the GPU, so they can now be scaled independently, depending on the application needs. If you need more storage or more GPUs, you use the network to connect the right mix of compute and storage for the application. And this can dramatically increase the efficiency and flexibility of the GPUs in a data center. Faster wire speed is not the only answer to feeding GPUs the data they need, however. To get the highest performance, we also need to use faster protocols. NVMe protocol on the SSDs is designed for NAND or other persistent memory devices unlike legacy hard drive protocols sometimes on SSDs. On the network side, NVMe over Fabrics was designed to move NVMe protocol across the network with as close as possible to the local NVMe performance. This is why the standard for NVMe over Fabrics was first released with RDMA as the network transport protocol. RDMA is the remote version of DMA, direct memory access. This is a hardware-driven transfer of data from memory to memory within a computer system. RDMA is hardware-driven memory-to-memory transfer across a network performed by the InfiniBand or Ethernet adapters hardware. You can easily see the performance differences with Microsoft SMB that supports both RDMA and TCP transports, or TCP modes, or standard Ethernet without RDMA modes. When RDMA is turned on, the performance doubles, the latency is cut in half, and the CPU utilization drops by a third. And you can watch a live demo of this on YouTube of the Microsoft event at the URL on the bottom here. No longer a niche technology in HPC, NVMe over Fabrics and hyperscalers have made RDMA mainstream. All the major OSs, whether it's Linux, Windows, VMware, now support RDMA, and all major protocols now have RDMA versions. And the new persistent memory technologies like 3D XPoint are using RDMA to connect applications over a network as well. This is an example of the performance you can get with NVMe over Fabrics over RDMA. This performance test used the NVIDIA Bluefield DPU single-chip JBOS solution in a storage target driven by two NVIDIA ConnectX 500 gigabit NICs. As you can see, very high IOPS at very low latency using almost no CPU cycles. Basically, local NVMe SSD performance across the network. Now that we have high-performance networking connectivity to the GPUs, how do we enable the applications to use it? And the answer is Magnum.io. Magnum.io is NVIDIA's set of APIs that integrates computing, networking, file systems, and storage to maximize I/O performance for multi-GPU, multi-node accelerated systems. It interfaces with the GPU software CUDA libraries to accelerate I/O across a broad range of workloads from AI to visualization. And you can learn all about this at the URL at the bottom of this slide as well. One of the technologies that powers Magnum.io is called GPU Direct. Using GPU Direct, multiple GPUs, network adapters, and SSDs can directly read and write CUDA host and device memory. This eliminates the unnecessary memory copies and dramatically lowers CPU overhead and reduces latency. And it results in, of course, significant performance improvements and data transfer times for the applications. Part of GPU Direct is GPU Direct Storage, and this enables a direct path to transfer data between GPU memory and storage devices like the local NVMe SSDs or remote ones using NVMe over Fabrics. Again, if you wanted to learn more about either of those technologies, there's URLs to very deep explanations. So an example of GPU Direct. So without GPU Direct, storage data is moved from the SSD into the memory of the SSD driver on the network storage, then moved to the memory of the network stack. Then the network adapter sends it across the network where it moves into the network stack of the GPU's host CPU, which then moves it to host memory where the application can now move it to the GPU memory. With GPU Direct Storage, most of those data moves are eliminated, and the data is moved with the network adapter's RDMA hardware directly from the SSD driver memory in the storage system to the GPU memory in the host. This increases the performance of the GPU application dramatically. This chart was shown by Chris Lamb of NVIDIA at a keynote at Flash Memory Summit last year, and you can see about a 10x increase in the performance using GPU Direct Storage. And you can watch this talk on the URL at the top of the graph there. Last, let's look at how GPU Direct Storage, 200 gigabit networks and RDMA, and the RDMA inside Magnum.io can help improve the performance of a machine learning application like the recommender on my first slide. Merlin is an NVIDIA deep learning application framework. It is designed to simplify the complexity of developing recommender systems. It enables low latency, high throughput production inference and can support training data that can reach petabyte scale. Magnum.io interfaces Merlin to the storage, and the performance you can achieve is really amazing. In basically minutes instead of days. And you can hear all the details on Merlin from Jensen, our CEO, on the link above the performance chart, again from his keynote at the conference last week. And finally, what does the future look like for GPU data networking performance at scale? Can it keep up with this continuing increase of AI and ML data requirements? Here are the industry roadmaps for Ethernet and InfiniBand, which clearly show the answer is totally yes. On the network adapter side, 200 gigabit Ethernet and InfiniBand adapters are in the market now. 400 gigabit is already in the market for switch-to-switch connections, and 400 gigabit adapters are on the near horizon. And with that, I'm going to turn it over to Celeste from Wick.io to talk about the next layer up.
Thanks, Rob. I think you have to give it to me, and I can give it to Celeste. Let's see. Here we go. Go to the next slide. Okay, Celeste, it's all yours.
Yeah, give me a second. Mike, how do I go back?
Maybe I'll use the down arrow to go back.
Oops, yeah, got it. Hey folks, my name is Shailesh Manjrekar. I head AI and Strategic Alliances here at Weka. If you don't know a whole lot about Weka, we are a parallel file system designed grounds up for NVMe flash. And essentially, we provide a similar kind of parallelism which matches the GPU layer parallelism. And that's because the stack is architected pretty much grounds up for this kind of new applications. We use our own real-time OS, which provides you almost zero copy architecture, the lowest latency, and the highest amount of throughput. And that's the reason why you see us having the success with HPC and AI applications. We are part of the NVIDIA NPN network as a solution advisor. In fact, NVIDIA is one of the strategic investors in us, along with HPE and several other strategic investors. And then what I'm going to talk about is take the thought which Rob kind of started with a little more kind of level it up and talk about, as you guys saw, whether it be accelerated computing, whether it be GPU computing, whether it be deep neural networks, it's really all about the data set. So data is really your new source code, and it's your strategic asset. So what I want to focus this talk on is essentially on three parts. So first and foremost, what are these changing applications where we see them, either in HPC, in high performance data analytics, or in AI ML. These applications are inherently different than the traditional file-based applications we are all used to, which were more contention-based, multiple reader writers, and so on, read, modify, write. AI/ML DL applications are very different. These are pipelines, and each of the stages of the pipeline have different storage and IO requirements. So we'll talk about that. As a result of these applications, the underlying architectures are changing. Edge is becoming is going to play a very prominent role. And we see these pipelines almost catering the edge to core to cloud, and that's become a requirement. The other thing which is happening is the compute layer is becoming extremely fast. You probably saw the announcement from Jensen last week about DGX A100 based on the next generation of GPU. It's almost 5x faster compared to its predecessor. You can partition it with 56 applications running the whole pipeline. To sum up, it suffices to say that the compute layer is becoming extremely parallel, and that's kind of driving the need for next generation technologies like GPU direct storage, which Rob talked about. Now, Weka is one of the only storage providers which is part of this GPU direct storage program. I'll talk about that a little bit more. And then finally, as I said, we want to make this all about your data set, how we are able to help you derive actionable intelligence out of that data, how we are able to operationalize the data sets for you, and how we are able to provide you governance from those data sets. Okay, so that's going to be kind of the key takeaways from my presentation. So where do we see this? So we see obviously the high performance computing market been penetrated with this accelerated compute with the likes of, whether it be Monte Carlo simulations, fluid dynamics, whether it be life science applications like, genomics, or what we call next generation sequencing. You would see accelerated compute or GPUs being used to accelerate those pipelines. The second vertical where we see GPU computing penetrating is high performance data analytics. If you watched Jensen's keynote, you would have heard about several different announcements in this area. So Spark 3.0 is now GPU accelerated with the Rapids accelerator. And now you are able to do an end-to-end pipeline for data analytics, right from ETL processing to your training, to your inferencing, all of that on the same GPU compute layer. And then finally, you see AI/ML been penetrated. One of the major reasons for the popularity of AI/ML is accelerated compute or GPU compute and the availability of the data set and the access it has to these data sets, right? Which is primarily determined by us, we as in Weka being the custodians of the data set, and the faster networking, which Rob talked about. So this is an example of what I mean by the new kind of applications, and not to overwhelm, but just to show you what is an edge to core to cloud pipeline. So here in this example, an autonomous vehicle is an example of an edge. And this is an vehicle with LiDARs, radars, computer vision cameras, driving on the streets and spitting out almost 2 petabytes of data sets per year per survey car. So you can imagine the humongous nature of the data sets. So the requirement is not just performance, but it's really performance at scale. Another point to note here is invariably there is this edge aggregation point where all of the edge data is essentially put together. And that's where Weka plays. So Weka does not play so much on the edge endpoints itself, but it very much plays on the edge aggregation, where you would basically put put and Weka together on an EGX platform, for example. Okay. Then there is, and the edges or the edge aggregation is all about training or ETL processing. Then there is a core where you typically would see DGX supercomputers or GPU computers, and Weka plays extremely well there for training purposes. And then finally, you will also leverage the economies of scale on the cloud where it's relevant, and there that it's the HGX from NVIDIA. And we work in the cloud as well. We are available in the AWS marketplace, and you can run us as a software as a service. So no matter where your pipeline is, whether it's edge, whether it's core or the cloud, you will see us being deployed with the same look and feel, the same performance and latency advantages we can provide. And we can uniquely cater to the end-to-end pipeline, right, to this varied storage requirements. Somewhere you're doing ingesting, which is all about write bandwidth. Somewhere you're doing ETL processing, which is more about random read writes. Somewhere you're doing training, which is all about random reads. And then you're doing inferencing, which is all about low latency. So you need a storage layer which can cater to all of these varied requirements. If you don't do that, you invariably end up into storage silos, which results into delayed time to value, time to market, and so on. Okay? And then you have on the top, if you see, you have this massive GPU farm, all orchestrated through a Kubernetes orchestrated layer, and the data sets transforming through each of these pipeline forms, where you're ingesting, you're labeling that data set, you're running training, and so on and so forth. So that's what I mean by the changing landscape of the pipelines. Then there is also use cases moving from the first generation of AI, which were primarily around computer vision, to the next generation, which is more around conversational AI, which is multimodal, which is NLP, NLU. And what this means is those DNNs are becoming a lot more complex with several billion hyperparameters. Take examples of BERT and Transformer and Megatrons. So they are becoming a lot more complex, and they are driving this several petaflops of compute power. Okay, the other example of how the underlying architecture is changing, as I said, edge to core to cloud is becoming very prominent. Edge and edge AI is becoming extremely popular and is expected to be even bigger than the cloud. And in fact, EGX platform, which NVIDIA launched, is primarily to cater to that edge cloud. Okay. Then there is a training part, which is where you're doing edge aggregation. And then finally, the core or the cloud, which is more around training. As I said, what GPU computing has done has really densified that compute layer. What I mean by that is, you're certainly moving from an Skylake processor, which used to have 24 or 48 cores, to a Tesla V100 and now A100, which comprises of 5,000 plus cores and tensor cores. So that has made the compute layer extremely parallel. And the traditional NAS solutions, they fall short when it comes to catering to this compute layer. You need almost a newly architected storage tier. So what it does, what all of these pipelines do, the storage tier or the storage layer or the storage IO is depicted in this slide. So when you look at the pipeline, somewhere you are ingesting data, that's all about massive write bandwidth. Somewhere you're doing ETL processing, you're labeling that data, which is all about random read writes. Somewhere you're doing training, somewhere you're doing training is all about massive read bandwidth. You're doing a validation or simulation of those DNNs, where it's expected to have a large number of streams from the storage layer. Then you're doing inferencing, and then you're doing lifecycle management. Inferencing is all about low latency. Then the DNNs, by far, they are mostly black boxes. So the only way you can find out why an autonomous vehicle turned left when it was supposed to turn right is by keeping a tab on those data sets. So versioning, what we call with data set, is extremely important. Weka has been able to very effectively demonstrate versioning with what we call reproducible or explainable AI. Okay. And we are in a really unique position to be able to cater to this whole data pipeline due to our mixed workload capabilities, our handling of small, big, large data files, whether it be low latency, whether it be high throughput requirements, and the data management requirements. We meet them very effectively. Okay, so with that, Weka AI is industry's first software-defined solution blueprint. So what we have done is when we talk to these new personas, whether it be data scientists, chief data officers, it's not enough to say, hey, we are the world's fastest file system in the world, right? Which we are, right? We hold the highest performance benchmarks for spec SFS, for IO 500, for images per second, for stack. But having said that, we wanted to make this all about your data. And we've been working with the best of breed ecosystem partners. So we don't lock you in, unlike some other storage vendors. We provide you the flexibility of working with the ecosystem of object storage vendors, and we work with object storage in a very unique manner. What we do is we extend the file namespace onto the object store. So we leverage the performance of the NVMe flash and the economics of the hard disk drive and the object tier. But we also work with the likes of NVIDIA, with HP, with Supermicro for that compute tier. We work with NGC Hub and Kubernetes orchestration. And then we work with accelerated libraries, whether it be Rapids, whether it be Index for HPC visualization, whether it be software in loop and hardware in loop training, and then go a step further by working with these SDKs like Parabricks, primarily targeted to solve genomics problem, Clara, targeted to solve a healthcare problem, and then Velohai, which is a partnership we have formed where we are able to show an end-to-end pipeline, whether you're ingesting data, you're doing data transformation, you're doing hyperparameter optimization, you're doing inferencing, all on top of Weka.io. Okay, so this helps us articulate the value proposition better. Hey, can we accelerate your pipelines? Can we reduce your epoch times? And so on and so forth. Okay, and then also make it easy to consume for our channel partners. Finally, to sum up, the keynote was an plethora of announcements, and Rob talked about it. I'm not going to again repeat some of this, but a next generation of building block, which is a DGX A100. Extremely fast kind of an GPU server, but also can cater to 56 applications. GPU direct storage is one of the enablers for a lot of the things which Rob talked about, whether it be recommender systems, whether it be conversational and multimodal AI, whether it be new SDKs, whether it be automated driver system. We are one of the only 2 vendors who are part of this GPU direct beta. So reach out to us if you have any questions and so on and so forth. But a lot of newness and new announcements happening in this space. I'll really quickly go through this. What we do is we break the silos with all these new personas. We provide you operational agility, and then we provide you governance with a very unique value proposition around encryption, end-to-end encryption, whether it is in flight or at rest. We work with leading key management systems like HashiCorp Vault to provide you that. One of these customers was able to achieve 80% reduced epoch times when using us. I will talk about explainable and reproducible AI. As I said, the ability to do versioning for these experiments is becoming extremely important from a data management capability perspective. We are able to provide that very effectively. We are able to provide hybrid workflows. GPU direct storage, as I said, as Rob talked about it, we are able to provide 80 gigabytes of throughput to a single DGX2, to a single mount point. That's what is important, right? We can scale to several gigabytes of throughput, but when it comes to a single mount point and compare that with an NFS scale out NAS, all flash NAS, you'll at the most be able to get 1.5x to 3 gigabyte of throughput. So we are able to showcase 70 to 80x higher performance with GPU direct storage. Okay, all kind of marquee performance benchmarks. We are the leading ones in all of this. These are the use cases which we go after. 3 prominent ones: genomics, AI, machine learning, and financial. We have marquee customer wins in each of these segments, and then also we work with HPC and manufacturing as secondary use cases. There's a bunch of collateral. We've been working with HP for putting out some of these collaterals. Here is the Parabricks solution, which is essentially for genomics, GPU accelerated framework for genomics. we've been the highest benchmark holders for STAC, Securities Trading Council, which is used by fintech and banks and quants and algorithmic traders. These are some of the customer wins across the board, and with that, I'll hand it over to Young.
Thanks a lot, Shailesh. Young, let me get you set up here. Okay, Young, you should have control now. Thank you.
And sorry, it said I was muted there for a second. So my name is Young Pak. I'm a senior director in product planning at Samsung. And the important thing to realize is Samsung is obviously a very, very large company. And I work for the part of Samsung that is often referred to as DSA, or Device Solutions of America. And this is actually a very important part of Samsung. It's the single largest part. And it makes the memory devices. And Samsung considers both DRAM and NAND as memory. So if we take a look at the different kinds of products that Samsung sells, why does Samsung care about AI? Well, as it turns out, there are basically no companies who are more interested in AI than Samsung. And it's actually for two reasons. Number one, we provide a lot of the basic technologies to create AI. So you see here that we make DRAM. We make the DRAM that goes into servers, and we make the SSDs that go into servers. The thing about this is that we pretty much service the entire industry, and we're the single largest provider of both DRAM and SSDs to the industries. And in particular, the memory that we sell to the GPU manufacturers are the ones that are going into the machine learning systems. So NVIDIA and AMD and Intel, they all have GPUs. They all are relying on higher speed memory, and this is a big part of the business that we have. I'm not going to focus on that part today because the panel is mainly about the storage part. So what I'll really be focusing on is just the storage part of our product line. So on the left-hand side, you see that we make a lot of the basic components that go into AI. On the right-hand side is the sister parts of the Samsung family. These are the mobile, the televisions, the appliances, computers, and et cetera, that everyone is buying today. They all are relying on AI. So Samsung tends to be a big consumer of AI in today's markets as well. So let's just take a look at storage and kind of what sets it apart from different spaces. So if you take a look at the middle here, there's a section on machine learning. And the general trend towards machine learning is more and more data. You may only have a few gigabytes of data. You may have a lot of data. You may have a petabyte or more. And a lot of people will come to me because I tend to work with all of our customers pretty much throughout the entire spectrum. I work with our hyperscalers, our OEMs, even national labs. So when I speak to them, I talk to them about what kind of problems they're trying to solve. And in general, you will find that the amounts of data that they're trying to process are increasing. And much as we've seen earlier, the speed at which these things are getting processed are increasing at a very quick rate. And we have very good visibility into what's happening with the memory on those GPUs, and we know that it's going to increase even faster just on the hardware side. And that's not even including what will happen on the software side. So what this is basically meant is when you take a look at machine learning today, you need to take a look at what those storage systems are going to look like. And there are two basic architectures that we can look towards. We can look towards the big data type architectures, or we can look to HPC type architectures. And what we have seen in the past is that big data tended to be scale out. That is probably the single biggest differentiator between big data and HPC. You can scale up your compute, you can scale up your storage, you can do those together, and it's relatively easy to do that. HPC is not like that. HPC tends to require you to focus your compute in the fewest number of nodes possible, and you have to be able to scale out your storage according to that. That is a big, big differentiator between the two. What we have found this to mean is, in general, you actually need to separate the space out. And small-scale machine learning, this is on the order of terabytes or maybe tens of terabytes, will go towards the big data. And the ones that are getting to the hundreds of terabytes and petabytes will go to HPC. I myself am working with a couple of our customers that had multiple petabytes of data, upwards of hundreds of petabytes of data. And when they've taken a look at their requirements, they cannot satisfy those requirements with hard drives. And that's why we're working with them, because they really need to be able to get all of that performance out of it. So to understand why SSDs are kind of necessary, we should take a look at what HPC storage looks like today. And this is a representation. It's no single model, but it's kind of an idea of the way that HPC storage looks. You're going to see a bunch of NICs, right? No longer are we dealing with a single NIC anymore. You're going to have at least a few, maybe as many as 6, I've seen. CPUs, you need the highest end CPUs to be able to process the data. And that is very, very important because today you need to have data security. You have to make sure your data is safe. So you're going to want something like RAID or erasure coding in there. And then on the right-hand side is high densities of storage. And the standard model today is to put 24 NVMe drives in a single chassis. So this is what a modern HPC server looks like. And they're all beginning to move towards the latest of everything. The latest CPUs, PCIe Gen 4, 200 gigabit NICs with RDMA, either RoCE or InfiniBand. This is by far the most common architecture that I'm seeing. And with that, we have this drive, the PM1733. It's shipping now. We are actually selling this in very high volumes to a lot of companies that are in need for HPC type storage. So all of the big supercomputer projects, all of the people doing machine learning at large scale, this is the kind of drive they're using. And this is by far the most popular that Samsung has for this space. So it's a pretty standard drive in many aspects. It's PCIe Gen 4, can go back to Gen 3, anywhere from 2 to roughly 15 or 16 terabytes of storage. Read bandwidth depend on whether you're using PCIe Gen 3 or 4. Could be 3.5 to 7 gigabytes a second of bandwidth. And similar numbers for, or half those numbers for writes. And then the read latencies are, on the order of 25 to 100 microseconds, depending on whether you're using reads or writes. So this is the storage of today, and it is how things work. But Samsung isn't trying to stand still, right? We have to take a look towards the future. And what we are finding is that a lot of the different companies out there are now being limited by the amount of bandwidth that they can get with the existing architecture. So we are developing new technologies, and these are the ones that we are working with some of our customers on to make sure that they're going to fulfill the requirements of the future. And we have two different directions we're going to go with two different products. One of them is in computational storage devices. When you take a look at computational storage devices, these are the ones that are moving computation into the SSD. With Ethernet SSDs, it's a little bit of a different story. We're just trying to simplify the deployment of these things. We're trying to simplify whether or not you need all of that extra computational work. So let's take a slightly deeper look into these. If you take a look at that previous model, it looks very similar to what we have here. The major difference is that we have now put some compute into these SSDs. So rather than just having a simple block device, we can now have smart devices. And what this will allow you to do is to process your data while it's still in storage, possibly at much higher bandwidth than you could do going through a CPU or going all the way out to a separate server. So this is a project that we have now. It is in beta with quite a few different customers, and we're testing now all of the different use cases. So if we want to take a look at the design of what a smart SSD looks like, on the left-hand side here, you can see that there's what looks like a fairly standard SSD chassis. This is in a U.2 form factor. What we've done is we've put an FPGA inside of this, and there are 4 terabytes of NAND in here. There's some DRAM in here as well, and this allows our customers to process the data while it's still in the drive, maybe not to completion, but at least partially, all the way to the CPU. The idea behind this is that there is a ceiling on CPUs that you have with every system, and by being able to move some of the compute into the storage, you'll achieve much better scalability. So rather than dealing with only the CPU being able to support that compute, you can move some of that into the SSD and be able to get much more linear performance. So on the right-hand side, we have a number of partners that we're working with on the software side to be able to put some IP into those FPGAs. We have some companies, some partners that we're working with that are putting solutions on to be able to accelerate Spark SQL. So if you're doing something having to do with a big data workload in Spark, you can push down your predicates all the way into the device, process the data inside the SSD, and then bring out kind of the net results of that. So that's a very interesting technology. You could also do video transcoding. So you may have a video file that is in one codec, and you might want to transfer it into a different codec on the way out. And then, of course, there's decompression, which is a very popular one as well. So rather than bringing your data to the CPU to decompress, you can decompress it on the way out of the SSD. That saves your CPU cycles for other workloads. So this is the smart SSD. And then we also have the Ethernet SSD. And if you recall, the previous design of the HPC storage systems included a bunch of NICs. It included CPUs, possibly other things in here. And the Ethernet SSD is made to simplify a lot of that. So rather than having all of those components, you can have just SSDs that have a direct Ethernet connection out to a switch. That switch can now connect out to other servers. And this will really simplify deployments of large-scale systems and hopefully reduce costs for TCO. We're currently prototyping these right now with a number of our partners. And this is getting to be of a lot of interest. The larger the scale, the more the interest in Ethernet SSD. And that's kind of all I had for myself. My name is Young Pak. I work at Samsung. So please get in touch with me if you're curious about any of these things. And with that, I'll relinquish control over to Daytera.
Thank you very much, Young. Let me pass you, unmute you, and let me pass you control here.
Thank you, Mike. My name is Keith Clare. Hi, I'm CEO of Daytera. I'm going to speak a bit about the application space that we work in. We have done real-world deployments of machine learning systems, and we've learned a lot in that particular process. And I want to go through some details of our experiences and what we have learned from those. The most common question that we get is, what type of infrastructure do I need for machine learning? There's a lot of focus on machine learning aspects of this, especially when customers are looking at first implementations. Speaking from our experiences, we find that focuses tend to be on just the machine learning component, when in reality, deploying a system like this requires examination of a wide variety of factors. First factor, of course, is how is it going to work with my legacy infrastructure? Unlike a specific type of applications which are uniform, most companies have a significant amount of legacy information spread across a wide variety of IT systems. They want to be able to integrate that information into the machine learning process. And that can be a significant part of the overall effort and require a significant part of the infrastructure to implement. If you look at HPC in specifics, we find that many concepts that apply to larger HPC implementations can be scaled to meet the requirements of medium and large scale businesses. And I'll talk more about that in subsequent slides. A big concern is operating costs. We have CapEx costs, OpEx costs, and also development costs. All of these factors actually have an influence on the final architecture you choose for your machine learning pipeline, the network systems you choose, and the storage systems you choose. What we have here is a data size survey. It was collected from a number of data engineers, and the questions they were asked are, what is the largest data set that you've ever worked on? As you can see, most businesses have a relatively small data sets. This was a snapshot taken in 2018. They obviously have data sets which will increase in size over time, but the takeaway here is that most companies have experiences with only relatively small data sets. They need to migrate to larger data sets and larger capabilities, and they don't necessarily have the IT infrastructure to do that and the capabilities to do that. They need to manage that transition. They need to understand that data sizes will increase, and that's very commonly a struggle, especially when they have to integrate with existing IT systems. If you look at larger systems, and some of these data sets examples are on the right, we can see that companies that do genomic exploration, oil movie development, and log analysis have much larger data sets. Genomic systems require about 200 gigabytes per person to implement. If you're doing oil exploration, you could have potentially 4 terabytes of data per site you're exploring and per sample. If you're doing movie production, there could be 1 to 2 petabytes of data required to produce a movie. Sumo Logic claims that they analyze over 100 petabytes of data logs daily. These companies are at the high end of data exploration and machine learning. Most companies will fall at a level below that. For example, Yelp has an aggregate data size, at least based on their last estimates, of about 16 gigabytes. In their case, the data size is relatively small, but the data velocity is high. They need to be able to analyze, infer that data rapidly, support a wide number of users. Most practical problems fall between the hundreds of gigabytes to 50 terabyte range. And that's where we see most of the interest for these types of systems. Even given those sizes, the components that are required to analyze that data are very similar to those you would see for HPC. And we'll talk about that in some later slides. So if we look at the data flow in machine learning applications, we have a number of factors to consider. We have to look at where the data currently resides. And this is especially important for legacy applications. We'll see files distributed across a wide variety of systems. We'll see object databases. We'll see SQL and NoSQL data records, all of which are required to create value from the ML process. These systems will be stored in DAS devices and NAS devices. They need to be collected. We need to go through an ETL process where basically data is extracted, is transformed, and loaded into the modeling system. So what we look for here is the ability in the system NAS software to be able to connect to all these sources and to be able to support the ETL process. ETL for us consists of both the development process and the production process, the same way you would have a modeling process for machine learning, training, and then inference. And you need to view both processes in ETL to understand the capabilities required by your pipeline. ETL can be very difficult because of the variety of data sources, because of the lack of cleanliness in data. You can spend a significant amount of time and effort in the development of these particular systems. Having the appropriate type of hardware and infrastructure can provide a great economy in terms of producing a system that operates correctly. When you're doing modeling, we have DAS and NAS systems as well as for training. And then for inference, typically we see NAS systems being deployed. If you look at the data rates that are used across these systems, ETL tends to have a high amount of input data with small to very large objects being ingested, which provides some of the complications when you're looking at the storage that you need. When you're doing production ETL, you have the same type of mixes. When you're doing modeling, generally speaking, you have data sizes and data rates which are moderate to large. And then when you're doing training, you have data rates and data sizes which can be very high. Read-write ratios are what you would expect. For ETL, you have a high level of ingest, and so your write ratios are very high. When you're doing production ETL, you can see a balance between reads and writes. When you're doing modeling, you have a very high read ratio to write ratio. Training is very similar, and then when you're doing inference, it's highly variable. So what you see here is the need to have a storage system which can handle a wide variety of different patterns of data. And also, you'll find that based upon how you do development and production, you need to manage data silos in the proper fashion, because oftentimes you need to divorce those two processes either for data integrity reasons or for performance and development reasons. The simple view of ML infrastructure looks a bit like this. I mean, this is where people typically start. They have their data sources, which tend to be generally not well understood. There's the understanding that there's going to be ETL servers which ingest that data. The data gets stored into a NAS system of some type. There'll be GPU arrays and smaller GPU-based systems to analyze, do the machine learning training. And then at some point, there's going to be results and reports that are used to create the business value from all that data. A lot of companies begin by focusing just on the ML process, primarily because that's interesting. They want to understand what they can derive from their data in terms of value. They tend to ignore the ETL process because it seems more mundane, even though ETL can be one of the more difficult parts of the data pipeline. Assumptions are often that the network technology is homogeneous, when actually it can be highly heterogeneous depending upon where you're distributing data and who is using it. There's also the assumption that you can have control over all the data storage, which often you do not. And then there generally tends to be little consideration about data flow and data management until towards the end of the project. And that's a critical aspect that needs to be planned in from the beginning. A better view of the data pipeline and storage systems is to understand that ETL will be a major consideration and a hard part of the development cycle. Many times it can comprise 80% of the effort required to put together a system. And also many times it can actually handle the majority of the data flow. It can also, depending upon the type of data being collected, require the highest number of IOPS when you are actually doing production inference. Data sources can come from legacy files, they can come from legacy databases. Very often, if you have edge technology, you will be interacting with an edge provider, and data will be stored in buckets. They'll be using their pub/sub messaging infrastructures. They will be using other APIs to collect data. All of those things you have to be able to manage, and you have to have enough compute, and network, and stores in the ETL servers to be able to handle that data. Once the data has been put into a common data pool in the NAS, you're at a point where basically you can begin your training and modeling. We find that many companies can benefit from GPU arrays, even if they're small to medium-sized businesses, depending upon how quickly they need to produce models to achieve their business goals. We also find that being able to dynamically allocate resources between ETL and machine learning processes can be very useful in managing operating and capital expenses. For example, during the development phase, which can be GPU and bandwidth intensive, you may want to allocate additional resources to the developers. And then when you enter production, you will reallocate those resources to the inference process. And being able to do that dynamically can allow you to share resources and lower the overall system costs. The other important factor we find is pipeline automation. With the high volumes of data that are moving back and forth across these systems, without having some form of rule-based system to manage that data, generally speaking, you end up with a potential loss of data. You end up with a lack of performance. What we recommend doing is using an automated data pipeline, formalizing the data rules in code, and using tools such as Apache Airflow or other commercial tools to manage that overall process. The other big benefit of using these tools is that when you get data pipeline failures, you will have logs and information that can help you identify and debug the issues in the system. The other factor that should be considered here is scaling up and scaling down, potentially to cloud bursts. They're using cloud bursting to get to the cloud. We find that containerizing all of the applications and using an orchestration process such as Kubernetes can facilitate our deployments and allow you to more adequately use your valuable resources, including the development resources, across the entire data pipeline. When we look at the actual locations of data, we have to consider the developers themselves. The developers are a scarce and valuable resource. What we have found that providing them with their own GPU systems, GPU-based systems, and significant memories helps facilitate the overall development cycle. Time to market can be reduced, which means that you will have to have the ability to interconnect potentially a significant number of smaller GPU-based systems into your NAS and provide them adequate bandwidth as well. So there's lots of moving pieces in a real production level data pipeline. All of these pieces can take advantage of what would normally be considered to be HPC elements. For example, GPU arrays, such as NVIDIA's DGX systems. We will typically provide each developer with their own development machine. That development machine could typically have 2 GPUs, a terabyte of NVMe storage, and then a high bandwidth network interconnect. So we try and borrow from the HPC capabilities at the appropriate spots, even in systems that don't have to manage dozens or hundreds of petabytes of data. So in order to be successful when deploying a system like this, you have to survey both your current and your planned data stores. Oftentimes you have a lot more data stores than you originally anticipated. Virtually always these are heterogeneous unless you're building a system from scratch, which is a single purpose system. We have to understand legacy requirements at the inputs and the outputs. This is very important. They can drive overall system performance, and they also can drive overall effort required to deploy the pipeline. You need to understand the data velocity along the data pipeline. it's not always at the machine learning portion of the pipeline. It can be at other locations. ML training and inference loads are generally very hard to guesstimate. You need to prototype and make sure you have scalability here. The ability to have a storage system which can scale if you need, both up and down, is very valuable here. When you look at deploying these systems, you want to have a cost-effective way to scale, to adjust data velocity, connect to a wide variety of data stores, and ideally be able to collect to the cloud as well. Again, much of the data you're going to be using in these systems will come from the cloud, especially if it's IoT or edge-based data. Using the cloud can also allow you to cloud burst for training purposes, in case you have a bottleneck in that particular process, and it can save you costs over time because you don't have to deploy a maximal system, and the operating or capital expenses for that can be reduced. Generally speaking, you can aggregate your ETL service to take advantage of high performance interconnects. And that we find that NVMe everywhere works best, either in the development systems or in the NAS. Cost optimization is a big factor here. In order to reduce development time, we believe that providing high capability workstations to developers has a very short payback time, both in the developer cost. We also have compared the costs of having NVMe GPU infrastructure internally for developers against trying to do development in the cloud. Generally speaking, it takes less than 4 to 5 months of developer time to pay back the costs of these workstations. That includes the costs to connect them to a network system and to implement the NAS infrastructure to have them interact. You need to work with legacy data owners to determine access to their data and the quality. If you are getting data from the cloud, you need to watch out for data egress costs. In the end, I think that these can be one of the biggest factors in determining the overall effectiveness of your pipeline and the data rate that it can operate in. And it can also have a big influence on the cost of moving your data across the pipeline. Hybrid cloud models can be very economical compared to other models. Make sure that you're using containers and Kubernetes to enable that particular process. And make sure you automate the data pipeline. By having data automation rules instantiated as code, you can manage your data much more effectively. You can save a lot of operating costs, and you can save a lot of grief when it comes to determining how your data is being used and finding out if there's errors in data movement. For more information, you can go to the link. We talk about how to economically deploy ML pipelines and the type of costs that you might want to understand with regards to that. Thank you, Mike. I'll return control to you.
Thanks, Keith. Let's go ahead and jump into our questions then for the panel. So the first question is, there's perception that successful AI implementations require big iron compute and storage platforms. Can meaningful AI solutions be built for less than 7 figures? And I'll just let everybody jump in. Rob, why don't we start with you and then go to Weka and Samsung and finish up with Keith.
Okay, thanks, Mike. So of course, it depends a tremendous amount on the application. But in a DGX2, there's 16 GPUs, 30 terabytes of local storage, and 800 gigabit network adapters to expand that storage as needed. As a technologist, I'm not in a position to quote pricing, but a quick public web search says that that system I just described is about around 400K. So that leaves 600K to add network storage or maybe even another DGX2 So I think the answer for some applications is definitely yes. I'm sure at least two or probably all three of my co-presenters can comment on how much network storage $600,000 will buy. And we can't forget the software that could need to be added. Again, that will depend on the application. I think that it is the most important thing to keep in mind is the application. And I think it's safe to say that a recommender system at a cloud hyperscale level is probably not going to make the six-figure budget.
Shailesh or Young, do you guys have anything to
Yeah,
add to this?
absolutely. Yeah. So, one of the advantages what Weka provides is you really need that performance to keep those expensive GPU cycles busy, right? So you got to be able to provide the data sets to the GPUs in a timely manner. So that's the first thing we do. We are totally software defined, as have been kind of harping on, and that kind of eliminates the vendor lock-ins. You can use any storage server. It provides you all kind of flexibility when you're building up the storage stack. Thirdly, we amortize the NVMe flash cost by using object storage and hard disk drives. So the scales, what you see in this HPC and AI applications are humongous, and you really need an economical storage solution, which we provide. The fourth thing, Rob talked about the DGX2 servers having NVMe flash. So with the deployment flexibility, what we provide, we actually are able to go onto the DGX2 servers themselves. Okay, so you don't need any additional external storage. We are able to leverage that 32 terabyte of NVMe flash within a DGX2 server itself. And you can have multiple of those for distributed training, and we can form a high performance file system layer across all of those. So that's how you absolutely can, do an AI implementation, which is a lot more economical.
Yeah, so I would add to all of this by saying you kind of need to set some expectation as to what the costs are. You have to understand a little bit better what kind of hardware you're going to need. So one of the things I will suggest to people is take a look at the amount of data that you have and how fast you actually need to process it. And that gives you a good baseline to understand the kind of hardware you're going to need. So if you have a 1 terabyte problem and you need to process it in an hour, it's a pretty low performance system. It's not going to be that expensive. If you have a problem that's on the order of 100 terabytes or a petabyte and you need to process it in, say, 6 hours, you can actually do some math fairly quickly to figure out how much that is. So as an example, I've done the math fairly quickly here. Let's say that you have 100 terabytes of data and you want to be able to train your system in about 6 hours. That works out to about 4.6 gigabytes per second of bandwidth. That's what you're going to need on the GPU side. That's what you're going to need on the storage side. So 4.6 gigabytes per second on an SSD is not that hard to get, or a large array of SSD is not that hard to get. But this is just a baseline. And what you have to then do is also multiply this by, well, how many people are going to be using this at the same time? Are they going to be running experiments? It just gives you a good idea as to how to scale this and what kind of storage and GPUs you're going to need.
Yeah, absolutely. In the end, it depends on the scale of both performance and storage. I would say that at the seven-figure level, you can handle probably the majority of ML processes for medium-sized businesses out there. When you get past the 100 terabyte level, then costs, of course, will be different. But basically speaking, most companies that I've seen can put together an ML system for well below that number.
Mm-hmm. It all is kind of driven by the data set size and how fast you want to have it, right? I guess it's kind of the two trade-offs you have, right?
Yeah. The other thing I would add to this is if you're trying to do machine learning to reduce cost, most of the projects I see out there are not about reducing cost. they're mainly about finding a new way of doing business. So you have to take into account not just what your TCO is, but what is your opportunity, and then figure out, is it really worth it for me to take on this project? If you're going to take on a 7-figure or 8-figure project, you might actually make more revenue, and that can justify the cost. But this varies depending on the company.
Absolutely. So with that, let's go to the first audience survey question. I'm going to launch the polling on this, and the question is has your organization explored and or deployed AI-based systems for business intelligence yet? This is a check one. And with that, the polling's open. We'll let it run for a couple minutes. I'm going to go to the second panel question. And that question is, data management is a significant issue in building and maintaining AI models. What are some of the best practices for managing data sets for AI? We'll start with Weka, then go to Samsung, and then Datura, and then NVIDIA. So
yeah, Mike,
go ahead, Shailesh.
Yeah, thanks for that question. So yeah, you are absolutely right. So, we tend to talk a lot about performance, and performance is absolutely essential for this data pipelines and time to market and time to insights. But equally important is what we've been calling explainable AI or reproducible AI, right? And what I mean by that is, as I said, the DNNs themselves are, for the most part, they are black boxes. So the only way you can find out what happened to that DNN, why an autonomous vehicle turned left versus right, why there was bias when there was a credit card application which was declined, the only way you can find the source to those errors is by keeping a tab on the data sets or looking at that data which was used for that particular experiment. So it's extremely important to keep a version control across both the compute side of things as well as the data side of things. And we do that very effectively. We in fact just announced a partnership with a deep learning pipeline management system called Volohai, which, as I alluded to earlier, enables us to showcase right from beginning where you're doing data transformation, you're doing the training and inferencing, and keep a tab on the data versioning by taking snapshots. So that's explainable AI. Reproducible AI is you can now go back after 6 months and reproduce that particular experiment and the data set associated with it. So data management is becoming extremely crucial when it comes to this AI/ML pipelines. And as you know, AI/ML pipelines, they're all about experimentations. There are several data scientists running this in one form or the other. Also equally important is the capability to form hybrid workflows across on-premise and in the cloud, and also be able to run in the cloud itself, which again, we do very effectively.
Excellent. Young, do you have anything to add to that one?
Yeah, so one of the things that I think is most important for people to understand is when you think about your data sets for AI and machine learning, think long-term. The problem that this poses is a lot of people will begin these projects and they don't have a real understanding of what they're going to do. They set aside some space on whatever storage they have, and then after a few months they realize, wait, how am I going to grow my data set? How am I going to expand my capacity? And then over time, this winds up becoming a bigger and bigger problem. So in general, there are two different strategies you can use to add capacity to your storage tier. And you have to kind of decide in advance which of these you really want to do. And it depends a lot on the scale, right? So the two strategies are, number one, you can decide I'm going to rebalance my data every time I add capacity. So let's say that you start with 50 terabytes of capacity and you start doing your training. After a few months, you need to add another 10 terabytes. And the problem that this creates is if you had your 50 terabytes that was, very evenly distributed on a lot of storage, and your new 10 terabytes is coming in the form of, one more SSD, you don't get enough performance out of that one SSD to fill your bandwidth requirements. So what you will have to do is rebalance your system. At that scale, it's probably manageable. 50 terabytes add 10, you can rebalance. It doesn't take too long. It should be okay. When you start dealing with hundreds of terabytes or petabytes, that is not not going to work anymore. So the other way that you can add capacity is to just ensure that you have enough bandwidth with the unit of added capacity. So let's say that now you're dealing with a petabyte of storage and you want to add 100 terabytes. You have to make sure that that new 100 terabytes can actually take the bandwidth load that you want. And it has a big difference in how you procure your hardware and how you actually deal with the addition of that added capacity. But these are very, very important things to think about early in your project because it's hard to switch.
Excellent. Keith, do you have any ideas? I'm sure as from a development standpoint, you guys have seen a lot of this where you have multiple data sets you want to keep.
Absolutely. Data management crosses a wide variety of different topics, and we've had a number of good points both on how you manage your training data sets and how you manage capacity allocation. So I'll talk a bit about how you manage data flow when you're doing inference and when you have to run inference and testing simultaneously. When you have huge volumes of data moving through the system, large numbers of files, a large number of training sets, a significant number of developers, unless you're able to codify data flows, understand where everything goes, communicate that effectively to all members of the team, everyone from the ETL portion all the way back into the report generation portion, it gets very difficult to understand the overall data structure of the system. Our experience is the best way to do that is to use a data pipeline software system that allows you to codify the rules of data movement and document them in that infrastructure so that you know where data is flowing at all times. You know when that data flows, because oftentimes data is temporal and you don't always do the same processing at the same time. So you need to have that time component built in. And then you need to have the ability to find out what happened when things break, because things will break. Some data flows will dry up. You'll find that there's a conflict. You may have to reallocate storage on the fly. Being able to track those processes and make sure everything is working is very important. And so just from an operating perspective, data flow management using the proper tools I think is essential for the long-term viability of your storage system and the data that's moving through it.
Very good. Rob, do you have anything to add to that?
I think it's well covered.
Very good. Okay, let's go to the audience survey question number 2, and I'll launch the polling on that. And that question is, what do you see as the greatest challenge for your organization to implement an AI solution today? This is a check all apply. Again, we'll give you a couple of minutes to answer that. We'll go to the final panel question. And that panel question is, when optimizing storage performance for AI training and validation, what factors should be considered? We'll start with Samsung, then go to Keith, then to Rob, and then finally we'll end up with Shailesh. So go ahead, Young, go ahead and take that one.
Sure. So one of the things that I think a lot of people don't realize when they start getting into this is that when you take a look at how machine learning in particular works, there are generally parts of the job that are parallelizable and parts that are not so easily parallelizable. So the act of creating a deep neural network is something that is very, very hard to distribute amongst multiple compute nodes. The impact that this has is actually quite huge because you don't want to take the things that can be parallelized and put them onto one of these servers where you have everything focused on a very, very high performance. So you want to separate out your jobs. Anything that can be parallelized and pre-processed in advance should be done on a separate tier of compute. And that's generally a lot cheaper, a lot easier to manage that way. Then you can reserve those DGX type servers for the actual training. And a good example of this is image recognition, right? I have some images that I want to recognize. I may have gotten some from the internet, or I might have gotten some from different sources. And in general, they'll have completely different resolutions, different color depths, all these differences. So before you can put them into real training, what you need to do is put them into a canonical format. meaning they all should be the same resolution. They should all have the same color depth. Everything should be similar. And rather than doing that inside of the deep learning machine, you do that on your compute servers outside, and then you can take that data and push it in. The other thing that this creates is the ability to kind of cache data, because if everyone has agreed on the exact same format, you can bring that data in, canonicalize it, then store that as a pre-processed version, and you can run many, many experiments off that version. And different groups can actually have different canonical forms. So the first thing to understand is that AI machine learning is not a simple thing, and you have to understand which parts of it can be separated out.
Keith, do you have anything to add to that?
Absolutely. I think a very important factor is metrics. Unless you have a sufficiently big budget where you can over-provision everything, you will have to live within the constraints of deployment. And until you start building out and running real-world workloads, you won't know what the data velocity is. You won't know what your storage capacities need to be. You won't know how much data is moving between different factors. You won't know the balance between inference and training and development time. You won't know how much system capabilities your ETL will require. You need to have metrics put in place. You need to take a look at the metrics, and from that information, you will be rebalancing and optimizing your system over time. You'll find that at certain times of the year or certain times of the month, based upon business requirements, loads will change. And you'll want to be able to reconfigure your systems to support those loads. So to do full optimization, it's sort of a continuous feedback process. You have to have the metrics in place to collect the information, and you have to have the ability to take those metrics and then go back and then reorganize your storage or reorganizing your network bandwidth or your compute resources to optimize the overall system.
Excellent. Rob, what do you think on this one?
I think that, I think actually maybe it was Keith who said on the last question that one thing that's happening more and more is migrating the workflow from the CPU to the GPU. And I think that as that occurs, you need to be very aware that you want to design your system in a way that enables the fastest and most direct path to the storage from both the CPUs and GPUs as these different parts of the process are moved around.
Excellent. Shailesh?
I can talk to, specifically when you're talking about training, it's about the massive read bandwidth which you can deliver to the GPUs or CPUs, right? And when you talk about validation, so I'm assuming you mean the simulation of those DNNs or simulation of conditions. So that's primarily where we see those is in the ADAS pipeline or autonomous vehicle pipelines, where you run a lot of simulations on those trained deep neural networks, where you are simulating conditions like a foggy roadway, there is a deer on the road, there is a pedestrian crossing, and so on and so forth. So in the first case, it's about massive read bandwidth. In the second case, it's really about large number of streams, where you are essentially providing those images to the simulation system. And then what the factors you need to consider is, obviously, NVMe flash becomes becomes very paramount when you're looking at that kind of performance. But the storage tier or the storage layer or the file system sits in between the really expensive GPUs and the expensive NVMe flash tier. So it is up to the file system to be able to take all of that performance and deliver it up to the GPUs and eventually to the application. So the file system has a lot of responsibility in that sense to be able to provide that parallel architecture where you're not becoming a bottleneck.
Excellent. Let's jump to the Q&A real quick. We have two questions that are related for Samsung, and those questions are, What is the programming model on the computational storage, and what are the form factors and protocol of the smart SSD products?
Right. So the computational storage or the smart SSD, the programmatic model is a little bit flexible. There are different tools that we have. There are some partners that we're working with. Not sure if I'm liberally to describe those today in this forum, but if you get in touch with us, we're happy to talk to you about which partners those are. You can also just use the product as is, as an FPGA module, and you know, if you're familiar with how to program an FPGA, you can do it that way. The form factors and protocol. The form factor is currently a U.2, so you can put it into any server that supports U.2. And the protocol, and I believe you're just talking about whether it's a standard block device. Today is a standard block device, and you know, you can just assume that it operates under that model.
Excellent. And then our last question is, then this one's specifically for Rob, I believe. During the NVIDIA presentation of the DGX2, there are a number of NVMe drives shown in the configuration, but the description showed them as NVMe RAID. What is the tool used to ride that NVMe RAID on top of the NVMe drives?
This sounds like an internal storage question, but I think I know the answer anyway. I'm from the network business unit